Good morning, good afternoon, good evening, everyone who have joined this webinar, and thank you so much for joining today's webinar. I would like to welcome Justin Azoff, who is a principal support engineer at Corelight, and he's going to present on don't be sad, make sure your input traffic is healthy. So let's enjoy the talk. Justin, take it away.
Sure. Hi, everybody. Hopefully this is helpful to a number of people. Unfortunately, if this is helpful to you, it means you have lots of problems, but understanding your problems is the first step to fixing them. So it's actually Don't Be Sad F. So why is it called Don't Be Sad F? Well, we need to do a brief history lesson. So in Zeek, we have our conlog for all connections. And one of the very interesting fields is the history field. And the history field is kind of a compressed view of all the different types of packets that Zeek saw. And the kind of ones we're going to be focusing on are S, H, A, D, and F. So you may or may not be familiar with the concept of a three-way handshake. So the three-way handshake is the client sends the SYN, the server responds with the SYN ACK, and then the client sends the final ACK. That's the three-way handshake. In Zeek, that will be presented as a capital S, a lowercase h, and a capital A. So for most TCP connections, or rather really for all TCP connections that are normal, for the most part, they should start with SHA. Sometimes you can have SHR, where if you do like a port scan, you'll often get an aborted three-way handshake. But for the most part, every normal, properly functioning connection will start with SHA. Right? So what if connections are broken and things are not working quite right? What if instead of seeing for each connection all of the client packets and the server packets, what if due to an issue with the input packets, Zeek was only seeing the source packets or only seeing the server packets, right? Just one side. Well, in that case, your history is going to be all uppercase or all lowercase, and sometimes all lowercase with a caret saying it was flipped, in that the first packet Zeek saw was probably from the server, right? If every TCP connection starts with the three-way handshake and the first packet Zeek sees is the second packet in the three-way handshake, something's probably wrong. So Zeek will flip it around. Sometimes it won't, and you'll get had. But these types of histories are a huge problem for Zeek to be working right. Now, there's many variants of good histories. Things will start out with some form of the three-way handshake and then some amount of data, ACKs, some combination of fins and resets. It doesn't really matter too much. The one that I did mention that's a little weird is sometimes you get an aborted three-way handshake. And bad histories will generally be all uppercase or all lowercase. Things can get a little confusing, a little outside the scope of this presentation, in that if your sensor is very overloaded, your CPUs are maxed out and you're dropping packets, or possibly your TAPAG is dropping packets or a span port is dropping packets, you could think of that there would have been the SHA, but if the H was dropped due to packet loss or overloaded, you will just have the S and the A. But that isn't this problem. That's a separate problem entirely. Another cause of weird histories that aren't half duplex are out of order packets. Sometimes due to very weird TAPAG setups or weird mirror port configurations, you'll get all of the client packets and then all of the server packets. So they should be interleaved, but sometimes misconfigurations happen and you just don't get them in the order that they occurred in. So this didn't start with the normal three-way handshake, but the packets were there, right? We still did see both sides of the connection. But the third cause, and what this talk is really focusing on, is you can have issues with span port configuration, tap configurations, or tapac configurations. And those will cause this across the board. So if you do have connections that are the kind of SAD or HAD connections, this is kind of the process that I've come up with to figure out what exactly is broken and how we might fix it. So it's primarily a 3-step process, starting with find the overall broken percentage. Then inside of that, find whatever the most broken thing is. Now, this is going to be the pair of hosts that have the most broken connections. It doesn't mean that these hosts are doing anything wrong. It's just going to be the pair of hosts that make the most connections. This could be a popular web server, a mail server, and anything that makes a lot of connections. And the reason why we want that is we want the most amount of information we can have. Two systems that might be important, but maybe they only make 10 connections during the day. 10 connections for statistics purposes is just not enough to really understand the problem, right? And then once we find the most broken thing, we see for just that, how broken is that one thing. So the way we do this is we could look at the histories, right? We could look for connections that start as SAD or connections that start as HAD, but things like out of order packets and drops complicate things. You'll get false positives. The thing I found that works the best is really just focusing on the counts of packets. So what we can do is look for all TCP connections, look for connections that at least on one of the sides had more than 4 packets, and we can bump this up to 10 if there's some false positives. It's kind of arbitrary. And then look for, of those connections, which ones had 0 on one of the sides. So if orig plus res was basically 5 or more and one side was 0, that means the other side had to have been 5 or more. And we don't care which side was 0, just that one side was 0 and one side was a fairly high number, right? So here's how you might do that sort of thing in Splunk. And I apologize for this being a little unwieldy. The gist of it is that you want to start with your conlog. You don't really need to be searching things like the DNS log or the SSL log. We only care about TCP because TCP has the 3-way handshake and should be bidirectional, where UDP might not be bidirectional, but that doesn't necessarily mean you have a problem. So just ignore UDP, focus on TCP. And then we look for, like we said, packets, sum of packets greater than 4, and half duplex will be when originating packets is 0 or rest packets is 0. And then we want to see what the percentage of that is. How many of these are broken versus how many of these are not broken. And if I did not lose my browser, which I full screened it, sorry. I have Splunk running here, and sorry, we can get that. Oop, I can't copy that. Sorry, I can't copy and paste from the slide because it's a slide, not text. Hold on a second, we can run that here and I could show you what it looks like because I just set up this Splunk so it doesn't have anything in it. We can bring up our search history, which should be, this one should work. Yes, we just need to fix that, fix that. So if we run that, sorry, that'll work. It should last all time. Sorry. Oh, this is what I get for setting up a new Splunk server just for this. Bear with me for just a second. There we go. So I do have the data. Here's a SAD connection. Oh, this is, apparently you cannot do that. If you try to set it to false, it does not work. So you can do no and yes. And I believe, actually, I think that's the other way around. yes and no. So this is the type of search you want to do and find out for all your connections for some time frame, what is the percentage that are broken, right? This is going to be the first step. Find out how kind of widespread this problem might or might not be. Ideally, the number of broken connections like this is under 10%, if not under, 5%, 1%. Anything over 25% will point to major problems with the traffic. So once we do that, that gives us the overall. And I have some examples here. I won't run this, but anyone that doesn't have Splunk, but you have JSON logs, you can use JQ. You could also use awk to do this. It's a fairly straightforward analysis. We're just looking for these values being big, these values being 0, and then overall, what's the rate of them? If anyone needs any help, I could always work out how to do this in different systems like Elastic and that sort of thing. So if you do have half duplex connections like this, what is your overall percentage? So I found anything under 10% is fairly good, and this might point to some isolated issues. One thing that has come up a couple of times is some advanced networks have set up things like direct connect tunnels to cloud providers, and sometimes that ends up set up kind of outside of the visibility of the security team, and that might not have been set up in a way that gives proper visibility, right? Where if it's your main internet connection that's not set up right, you don't get 10% broken, you get a huge percent broken. So under 10%, pretty good. You'll still want to dig into it to find out what's wrong. Under 40% is really not great, but I've not seen that too often. What sometimes that could be is kind of two, say, imagine like two buildings where one building is perfect and another building would be at 66%. So if you average those two together, you get a perfect building and a 66%, giving you an overall 33%. So the more complicated a network might be, that's why the next step of focusing on the most broken thing is so important, because on bigger networks, there's often pockets of problems where overall the architecture is fine, but you end up with particular subnets that just might not have their taps set up correctly. So 100% of that network is broken, but that network might only be 20% of your traffic. So the way these percentages interact is interesting. But one thing I have seen a number of times that's very, very interesting is there are certain percentages that show up over and over and over again that point to very specific problems, right? I sometimes call these like perfectly broken, right? So sometimes you get exactly or within maybe 2%, so 48 to 52% is broken, or 64 to 70%, that sort of thing. These point to very specific issues. So once we do that, like I said, the next step is find the most broken thing, right? This is critical for the cases where you do have two areas where one is okay and one is broken. We want to focus on the broken thing and find out how broken is the broken thing, because sometimes you do have a subset of the network that doesn't have proper taps, and that subnet or subset is broken 100% of the time, but the overall percentage just isn't very high. So how do we do that? So we can use similar query in Splunk, but instead of reporting on the percentage of broken connections, what we want to do is have it tell us what the top pair of hosts is, and potentially with the history. And I'll show what that looks like. It is probably going to be a pain, but we can do this again. When I was testing this out, I just copy and pasted, not realizing that that would stop working, but that's this search. So in this case, I didn't show history, and I had loaded in some data where this is the only broken thing. So in the case of this sample data I loaded, there's only one pair that talks to each other that is broken. And usually this is a first query, and then just as a follow-up to see what the problem looks like, you can add the histories, and in this case, you can see this one is always sad. So this tells us when the 10 address talks to the 192 address, we see the outbound packets from 10 to 192, but we don't see the packets from 192 back to 10. And then, right, so that gives us this pair of addresses. So what do we do with this pair of addresses? Well, the next thing we do, I'll skip over the JQ version, is focus just on that pair of addresses. So this is similar to the first search that we did. We're just adding in the two IPs as search terms at the beginning. So if we run that, my search history, I should have it, yep, right here. We will see that when these two IPs talk to each other, it is broken 100% of the time. So if you remember from the first search that I did, I think my broken percentage was like 30 something percent. However, this is telling us when this host talks to this server, we never see both sides, right? And that's a huge difference between something being broken a third of the time, right? What this actually tells us is a third of the time it's broken 100% of the time, right? Which is a very interesting statistic, right? If this also came back as broken a third of the time, right, then that's 100% of the time it's broken a third of the time. They're two very different problems that have very different causes. So because this never works, that points to just a total like gap in visibility, right? So now that we know that, let's skip over the JQ. But yes, you can do this in JQ just exactly like you can in Splunk. So a quick diversion. Sometimes you do this and you just don't have good data. Maybe the network is kind of not busy enough, right? Maybe you're trying to validate a new deployment and there's just not a lot of traffic, right? This could be like a greenfield data center or something that's just coming online. So an amazing thing that you can do that's really easy, it used to be hard, but now curl has this local port option, is you can do a for loop like this to generate, this generates 50 connections with sequential source ports in the range of 40,000 to 40,049 to, in this case, my server, which only has a single IP. So I know from a 5-tuple, this will have 4 of the fields the same and 1 field changing. And when you run something like this and extract out these fields from the con log, this is the sort of data that you should get. And I truncated it to just the first 15, right? But we should see a bunch of connections from these sequential source ports to port 443. Each connection is about 30 packets in either direction. We see both directions, we see both byte counts, and our histories are very healthy. If you do this on your network and you get something like this, well, now you have big problems, right? Some of these connections have zeros where they only saw packets in one of the 2 directions. And you can do this multiple times. And the really nice thing about this is it will be repeatable. If you ideally wait 5 minutes between tests and run this again, you should get the exact same result. Now, this is good because things like the system's being overloaded or dropped packets either on a monitor span port or on the sensor could cause you to have missed packets, but it's kind of going to be applied random, where this is consistent. So if you were to run this and you get that ports 40,002 and 3 are broken, if you wait 5 minutes and run this again, it should be broken the second time too, because almost all load balancing and hashing is going to be based on the 5-tuple, and we've told it to use a specific 5-tuple. So this lets you run tests multiple times and see, especially if you're trying to make changes and fix things, you don't have to worry about things bouncing around and being different. This will work the same way every time. And yeah, very, very useful for testing and understanding the problem. So what are the different kind of percentages and what are some of the causes for them? So if you do have 100% of your connections broken, it's obviously really bad, but good in that it's one of the more easy ones to fix. It means that there's just a fundamental misconfiguration somewhere with either a span port or a tap, in that imagine that this is a link between your core switch and, say, a border router or an internet router. It doesn't really matter, but this is the link that you want to tap. And if for whatever reason you have one direction tapped and the other direction not tapped, then 100% of your connections will show this problem. So not ideal, but pretty simple, pretty easy to fix. There's not too many moving parts here that can make this hard to understand. You simply just do not have all of the packets in one direction. Figuring out where the packets are going is usually pretty straightforward. It's okay. Another very common problem is that same issue, but applied multiple times, where you might have two core switches and two border routers where there's just this, like I said, this fundamental misconfiguration where people didn't understand that you need both directions, and it's been applied across the board, right? So same mistake in two places. Very common problem, but like I said, it's bad that everything is broken, but it's good in that it is usually the easiest to track down. So what is the usual cause for this type of issue before I go into more other issues? So here's a picture of a fiber tap that I have here that I took a couple of minutes ago. And it has this helpful little diagram that shows when you connect one device to X and one device to Y, if you look at the arrows, you have an arrow pointing to tap X and an arrow pointing to tap Y. And a very common problem we've seen for people new to taps is they will do something like this. They will take the output port, which is a duplex LC connector often, and they will plug it in to a duplex LC connector on a NIC or a tap-ag switch, something along those lines. However, if we go back to this diagram, these are both output ports, right? So both of these are trying to transmit. And if you look very closely on these SFP modules, there's these two little arrows, triangles. I guess they're not really arrows, they're just triangles, showing the direction that they expect the light to go in versus out. So the right way to configure a fiber tap directly into a switch or a NIC is you actually need to split it and connect both of the outputs into two separate inputs on two separate ports. This problem is extremely common for people new to taps, in that it's just very easy to not realize that you need to split the fiber and connect it to two different input ports, right? Because there's nothing actually being transmitted. You don't need to connect anything to the other side. So if you make this misconfiguration, effectively half of the light is being sent into the other transmit port on the module. So you have a transmit connected to a transmit, and that just doesn't do anything, and effectively everything is lost. So very easy problem to make. One time that this came up, just sort of a funny story, we were going over the taps and they said something like, yeah, we have two taps set up and we connected them to both ports on the other side. And I said, 4 ports, right? And they said, no, but both ports. And so I had to start asking some more detailed question and found out that they had done this exact thing. They connected the output port on the tap to one port on, I think it was a tap-ag device or something like that. So for every link that you have tapped, you actually need 2 NICs or 2 input ports on your switch or tap-ag device. Very, very important, very easy problem to make. And nothing really cares that you mess this up, right? If you're only expecting one port to come up, that port will come up. What you don't know is that you should have a second port. So this is the most common cause of tap related issues. So moving on, the other really common thing that we see is you get something like just about 50% of the connections are broken. So how do we have that problem? It's very common on larger networks that there is some form of redundancy. You have two core switches, you have two border routers, you have two something. And in this case, it might not even be two switches. It might just be two line cards on the same switch, right? You might be using a port channel just for added bandwidth. And a problem could be that one of the links is okay. So whoever set up the first one, both of these links are good, but on the other pair, one of those links is either down, right? It could be plugged into the wrong place. It could be a dirty fiber, any amount of causes. And when you do the math, right, there are both outbound paths are okay, but 50% of the time it uses one of the inbound paths that is not okay, and you get these half duplex connections. And they will always be that the inbound packets into the network are missing. So very common problem, and that's why finding the most broken thing helps a lot, because having that statistical information helps you figure out just why things are broken only some of the time. The next really common and interesting configuration that we see is you get 2/3 broken. And this is where things start getting really interesting. You imagine, right, you had one link that was tapped, and then you have another link that isn't. In talking with a lot of people, this comes up a lot when you have a networking group that's separate from the security group that don't necessarily always talk to each other. So imagine the left side was set up at one point, everyone is happy, and the networking team decides that they need more redundancy or they need more bandwidth, and they add another link, but they don't talk to the security team. So that new link that is now getting half the packets in each direction is not tapped at all. So the interesting thing is you might say, oh, well, so 50% of the things are broken, shouldn't 50% of the connections be broken? But if you look at kind of the table that results, there are 4 paths, again, like before. If we use the left path for both, everything's okay. But if we either go out the left and in the right, or out the right and in the left, we either get half duplex in one way or another. And finally, if we happen to use this untapped path for both, if we go out the right side and in the right side, our packets are going to be missing entirely. Now, when you do these reports in Splunk or something, it doesn't know that these connections are missing, right? You can't report on something you didn't see. So of the ones that you did see, 2/3 of them were broken, right? This connection is okay, and then we have the other 2 broken in 2 different ways, and that gives us 66% broken. And this is probably the most common misconfiguration that we've seen. Just as networks expand, things are often missed from the security side, and you get this problem. There's another very interesting cause of this that also happens to be 66% broken, but it is a completely different problem in that picture a network where all of your taps are fine. They go into a TAPAG, but the TAPAG device isn't properly configured to send both sides of the flow to the same sensor. So like before, there are 4 cases. We might get the inbound and the outbound flows sent to Zeek 1. That's okay. Zeek 2 in this case sees nothing. It's perfectly happy to see nothing. Then there are 2 cases where the connections are split. We might have the inbound flows to Zeek 1 and the outbound flows to Zeek 2, or the other way around. In that case, both sensors each log 1 broken connection. And then the final option is that Zeek 1 sees nothing and Zeek 2 sees both sides of the connection. And like before, if you add up the different problems, you will have, for every 6 connections, you will have 4 broken connections, which works out to that same 2/3 broken. So the cause is completely different, but the math works out the same, which gets very interesting. And I was actually on a call this week where we had this problem, but the math wasn't quite working out, and I was a little confused why. And then I realized it was because they had 3 sensors in the group, not 2. And in this case, you have 4 broken connections for every 5 connections that are logged, because there's just more sensors that things can get load balanced to. And actually worked out, if people are curious, you can work out the formula for how this works. It's really just that for every, if you have 3 sensors, you will have 1 okay connection, but the number of sensors minus 1, you can double that, and that tells you how many broken connections you have. So interesting enough, and this is great for testing if you think you might have this problem, and you can, maybe on a night or a weekend, remove all but one of the sensors from the load balancing group, because it's impossible to miss load balance when you only have 1 sensor. You will be guaranteed that that 1 sensor sees both sides of the connection. So this is sometimes not doable in all production environments, because if you truly need 3 sensors to handle a load, you can't put all of the traffic into 1 sensor. But sometimes you can, like I said, on a night or a weekend, to rule out the TAPAG load balancing as the problem. And you can see this escalates very quickly. Once you have 8 sensors, you will end up with over 90%. It's actually 6 sensors. Over 90% of your connections will be broken. So why do you have this problem? And this also ends up being very common. When you set up a TAPAG to do load balancing for the purposes of things like Zeek or even Suricata, you really need to only load balance on the 5 tuple. So, right, TCP or UDP, and then the IP addresses and the ports. Many TAPAG load balancing systems let you configure load balancing based on other attributes like VLANs, MPLS labels, DSCP values for QoS. But, and here's the critical thing, just because you use these technologies doesn't mean that these values are all consistent, and this will make things worse. And one example where we saw this was a network that used MPLS. Like, they legit used MPLS for their, I think it was their internet routing. I'm not 100% sure on that. But so in their TAPAG configuration, as far as load balancing, they had checked MPLS, which makes sense, right? You use MPLS, so you should tell your TAPAG to use MPLS. The problem was there was no relationship between the outbound MPLS label and the inbound MPLS label. So it was splitting all of the connections across 2 different sensors. Basically, another case of 100% broken, right? It was something like all of the outbound was MPLS 100 and all of the inbound was 200. So in that case, they never match. And if you group flows by 5 tuple plus MPLS label, it just never matches. So this is extremely common. We see the same thing with VLAN tags too. Sometimes based on where the taps or the span ports are, all of your outbound packets might have a VLAN, but the inbound packets might not, right? Because if your inbound packets are coming from the router, often that won't have the VLAN. So the nice thing in this case is the easy way to fix it is just keep it simple. Turn off every possible optional feature. It doesn't matter if you use them. All you need to turn on is just the basic IP 5 tuple fields, right? Especially you don't want MAC address, right? No VLAN, no nothing. Keep it as simple as possible and everything will work. And I think that's my last slide. There's one other thing I wanted to mention. I didn't have a slide for it. Over here, when I mentioned that there's a quarter of the connections missing, one way to understand this is if you generate connections, if you do this, you will actually be able to see the missing connections because you know you're expecting sequentially numbered connections. So in this case, if you have numbers missing, you know that you missed both sides. And this is really one of the only ways I know to figure that out. And it comes in very handy because otherwise, how do you know what you're missing if you're completely missing it, right? Missing half a connection, you can know because you saw one side but not the other. But missing both sides is really problematic because you otherwise don't know you missed it. So that's what I had for slides. I don't know if we have any questions. This is the sort of thing that's very interesting to go through live on real networks. Unfortunately, I just didn't have one handy I could use that didn't have sensitive IP addresses and things on it. But it is, every problem tends to be different. Where was I? Those percentages tend to be where are we? Oops, that doesn't go backwards, it goes forwards. Yes, these percentages do show up a lot, but they aren't the only percentages that I see. But it is always very good when you do see one of these because then you're most of the way on to understanding what the problem is and how to fix it. So yeah, I'd be glad to answer many questions or talk about some of these slides in more detail if people have specific things they want to know. I actually don't know if we have any questions. I don't see any in the chat. Let me think here. Yeah, I guess if there aren't any questions, I suppose we also could end early. I'm going to update the slides a little bit more and have some additional links and references before I share them. I realize there's a couple of neat things. Actually, there is one thing. Tim Wutulitz reached out. We actually worked on a Zeek script at Corelight that does this analysis just all the time using sampling. So there's not a lot of CPU overhead. So you basically just get a log that tells you what your percentage is. Like you can do it in Splunk, but if you do this all the time in Splunk, you have to crunch a ton of data. If you tell Zeek to do it on the fly, it's a lot less overhead. So he actually asked if we could open source it, and my answer is mostly, oh, I never thought about doing that, but we can certainly look into it. It's very similar. People might be familiar with the Bro Doctor package that I wrote. That it does still work with Zeek, and that was kind of the first generation of this where you install it on your cluster when you're having this sort of problem, and it tells you various things about your traffic, if it's healthy or not. And the idea was, well, could we do that where it just runs all the time? And that's what this new package does. That way, it's really useful because if you have unexpected changes made to the network where you might have very low half duplex and someone might make a change to the network and that might jump up to 50% and you might not realize, this way you could make an alert for that value, crossing a certain threshold. So that's kind of the ideal way to monitor this sort of thing is, get this problem under control and then monitor it and make sure it doesn't change. It's very easy to fix when you know exactly when it broke. I know a lot of companies are really big on things like change control. One thing we found really successful was being able to tell customers like, hey, on September 4th at 2 p.m., all of your traffic became half duplex. Did you by any chance do any maintenance on that day? And if so, what did you do? Right? Just knowing when something broke can help a ton for tracking down what went wrong. oftentimes it's, oh yeah, the network team, added a new router. And then it's, oh, did they maybe disconnect the tap and forget to reconnect it? And then you can get it fixed. So yeah, I think that's just about all I have without any questions, I suppose. Yeah, we could end a little bit early.
All right. Thank you so much, Justin. Are there any questions for Justin? I don't see any questions in the chat as well. So if people have any question, this is the time to ask.
Yeah, I'd imagine there might be some people watching that have never quite looked at this and might be discovering for the first time that they have this problem. And they might have questions maybe like 20 minutes from now, which I totally get. But I'll be on the Slack channel. People can definitely start a discussion there if they discover that they have this problem and might need to do some work to get it fixed or dig in to understand what the problem is.
Absolutely. So looks like we don't have any questions. And once again, thank you so much, Justin, for this amazing talk. And I'm pretty sure that people, this is very real world example like, so I'm pretty sure people will have questions and encounter this kind of issues in future. And then I hope this will really help them out in figuring out what the issues are, especially for the tap aggregation part of the of overall pipeline. So I think with that, we can actually end early, and the recording of this video will be posted soon on Zeek's YouTube channel. So people later on in future, if they want to come back to this webinar, they can come back and see the webinar online. So yeah, with that, I think we can end early. All right. Well, thank you so much, Justin, once again, and take care, folks. I'll see you guys next time in the next webinar. Thanks, folks.
Bye, everyone.